everyone to be back to our podcast, The Videoverse. And then this is going to be a very special episode. Lots of things different from the previous episode because this will be the first time that we have invited the academic people to join our podcast talking about video technologies. And it will be very, actually, I have been really looking forward to this episode. First, I introduce my co-host, Thomas. And he must be very familiar because he already been in one of our existing episodes. And then, so today we have Professor Maggie from Purdue University at West Lafayette, and we also has her student Zhihao to join us. And it's a very interesting episode in another meaning that Professor Maggie joined us from the East Coast of the United States. And then her student Zhihao right now is visiting China, visiting Shanghai. So he is joining us in Beijing time. Actually, we need to congratulate Zhihao because he just got married. And then my co-host Thomas joined us from London. And I'm here right now in the Bay Area observing the Pacific time. So right now we are actually really widely spreaded. So you can see that I'm here in the morning, and then we have London right now into the afternoon. East Coast actually already very bright morning, and then it's late evening in the Beijing time. So it's really show that we are very globally distributed in our podcast. So today we're going to again talking about video compression and actually about AI applied to video compression. But first of all, I'd like to have our guests to have some introduction about themselves. So Maggie.
Thank you, Zoe, for the introduction. So hi, everyone. I'm Maggie Zhu. So I'm an associate professor with the Almore Family School of Electrical and Computer Engineering at Purdue University, the West Lafayette campus. Very nice meeting everyone in this format. It is my first time, but I really look forward to it. So our group mainly work on research topics related to image processing, computer vision, video compression, as well as digital health. And the topic that we would like to discuss today is a little bit special. It is more of a emerging area and known as coding for machines. So the idea here is that more traditionally, we think about multimedia signals, not just videos. It can be speech, audio, images, or even point clouds, live fields, these type of signals that have mainly been acquired, processed, and compressed for the purpose of human use, right? But however, because of the increase of a majority of the internet connections and then traffics are now more dedicated to from the machine to machine type of framework. So how do we address this issue with increased data communication across network? And if it is served if it is for the purpose of automated machine analysis, then how do we think about this new problem, and how do we think about in terms of video compression? So this will be the topic that we're going to discuss today. So I'll let Zhihao to introduce himself now.
Okay.
Yeah, so hi everyone, this is Zhihao. I'm a PhD student, the third year PhD in Professor Zhu's group. And so as Professor Zhu said, we work on various things. And for me, I work on like coding plus AI. So in two ways. So we have coding with AI, so we can use like AI techniques to facilitate to improve coding performance, and we have coding for AI. So we can design coding algorithms specifically for AI algorithms, but not for humans. So this is my research scope. Yeah.
Well, thanks. You are still in your honeymoon. I like to add a little bit more because we invite Maggie and Zhihao, and then we need to congratulate them that they actually just won the best algorithm paper award in the just finished on the early January of this year in the WACV conference and think they can talk about it a little bit because it's actually the paper drew the attention to us because the paper is also talking about, as introduced by our guest, applying AI technologies to video compression and our image compression in the large. And it's has been, we also have episodes talking about how AI can be applied to video codec because right now machine learning has been widely applied to everywhere, especially recently there's a wave about talking about ChatGPT. And so um, there's AI machine learning can be applied to almost every aspect. But for image and video compressions, I think our guys will also touch that point. It's a very complicated, relatively complicated procedure. We also have prior guests talking about there's a lot of research ongoing, but a lot of people also hesitating that whether machine learning or AI could ever be applied or ever show advantages compared to the traditional 2D transform plus motion estimation and compensation platform. We talk a little bit deep tech here. So basically, image and video compression has a traditional framework that has been applied for all these many years. I think since the very old codec standard to the most recent one. For example, we now know that H.264, AVC, and then H.265, HEVC, now VVC, the ACA H.266, and on the other trend, the lines for open media that have AV1. All these video codec standard produce different formats, but underlying they actually follow very similar framework. The image compression similar. There's transforms applied to the images, and block-based prediction are being applied. So there's a traditional framework that has been leveraged down there, but how AI can or machine learning can be applied to down there. I think Zhihao just mentioned a very important ideas that sometimes image or video compression, not just making compression of the images to be seen by human eyes, but also can be applied for the ultimate goal for the image to be consumed by machines. First of all, I think Zhihao, you can talk a little bit about the title of your paper and the main theme of the paper that you have just won the best paper award. Actually, you also have one more paper that's won at least entered the top 5 best paper finalists for the December conference, Picture of Coding Symposium, short as PCS. I believe PCS right now is one of the most prestigious video and image compression conferences in academia as well as in the industry. So can you talk a little bit about the best papers work that you've done? Also, you just mentioned that there is machine learning applied to image codec part that for the sake for the image to be seen by the machines instead of my human eyes.
Yeah, so we have 2 papers published in the last 2 months, and so as we said, we have 2 scopes. So one is coding for AI, and another is coding with AI. And maybe let me talk about them one by one. So let's talk about the coding for AI. So so in this problem, so we are interested in we want to design an encoding algorithm that is optimized for for AI algorithms to execute on the bitstream, but not for humans to look at the reconstruction. So if we look at like all of the traditional codecs, like for images we have like JPEG, JPEG 2000, BPG, etc. For videos we have like H.264, H.256, AV1, and VP9, etc. So all of them are like compressing videos to as few bits as possible, and they want to reconstruct the image or video to the pixels to their original form, and we want them to have a good visual quality. So, but this this is very like normal in the past like 20 years, but now many video and many images, I believe, many data on the internet, they are transmitted not for human to look at, but they are used for machines to analyze. For example, let's say we have a drone, we have a unmanned aerial vehicle, UAV. Like it is it is operating on the sky, and it captures. There's a camera on it. It captures some videos, and we want to do some like, let's say, object recognition on it. So the way it works is it captures video, and it needs to transmit the video to the backend. It may be a edge server, or it may be a cloud server. So we want to do it because like running an AI algorithm on the on that on that UAV is expensive in terms of like power. So we really want to like compress it into bits and transmit into the backend for analysis. And on the backend, there's no human to look at that video. There's only like AI algorithm to analyze it. So in this case, we really don't care about the reconstruction PSNR. The metric we always use in video compression. We really don't care about it in compression. We just care about the AI algorithm's accuracy in the backend. So yeah, so this is what we call coding for AI problem. And we have one paper on this, and the second scope we care about is coding with AI. So as Zoe said, like in the past like decades, we like virtually all of the codecs are based on transform coding. And yeah, so in the past few decades, like to my best knowledge, virtually all of the codecs for images, for videos, they are based on transform coding. So there's a, let's say, DCT or DWT, like a discrete cosine transform, a discrete wavelet transform. There's a transform that transforms the pixels into the frequency domain, and we quantize and code the frequency coefficients instead of pixels.
Do these sorry to interrupt,
But
but
yeah,
do these AI algorithms work in
yeah, sure.
sort of similar ways, or are they a generalization of this kind of architecture? Do they have things like quantization and approximation in them?
Yeah, that's a very good point. So I would say it works a similar way, but it's more generalized, because if we think about the essence of compression, so the how compression works is that we can find like frequent patterns and infrequent patterns, and we assign fewer bits to frequent patterns and more bits to infrequent patterns. And so that is like how entropy coding works, and it is also like the fundamental of the foundation of how compression works. So
Yeah.
yeah.
Yeah, so I think one of the challenge with the traditional coding is because there's a lot of parameters to tune, right? And it is almost like an art that you have to master. And it becomes very difficult for someone to even try, to get into the area, because they will say, hey, here is the latest, greatest a standard that you can use, right? And then, go use it. But how, right? So there's a lot of a training that is involved, which is it is a lot of engineering design into it, and it is very dependent on the different applications, right? So that's why you have many different configurations, different kind of modes that are being introduced in the traditional codec, because it is tailored to achieve that best RD, for the type of applications or even content oriented, right? So I think this is one thing where AI techniques could help, or of course, this is just one aspect of it, right? What if you can learn something about this data? It needs to be compressed, whether it's image, video, or something else. But now it has the leisure of large-scale data sets. Right, so this is something machine learning can leverage. Is from the large-scale data set, then you can perhaps alleviate some of these burden on having to trying to manually find what would be the best solution for your particular application or the particular content. And if you think about it, this is not really a brand new idea, right? Because, for example, even looking at works such as quality metrics, right? There's the VFM, and then the reason why is because it sort of also knows about when PSNR works better, when SSIM works better, or when VIF works better. So again, it is leveraging on having seen a lot of different data, and then knowing when in what scenario would you use what type of parameters. So I think this is one of the advantage of introducing or including some of these machine learning and AI techniques in the coding pipeline. So that's just my 2 cents.
Would you say in these types of applications, these machine-to-machine applications, there's maybe a different kind of balance? I mean, traditionally, video codecs have been designed around a sort of one-to-many architecture. I mean, video conferencing is one-to-one, but in VOD you have a single encoder that can be very expensive because it's serving many thousands of decoders. So the balance is many decoders, a single encoder. But are these applications more where it might be the other way round, that there might be many encoders and a single decoder, something like surveillance or security or those kind of applications?
Mm-hmm. Yeah, exactly. So that raised a very interesting point, Thomas. Because if you think about it, it really depends on what kind of applications and then the type of hardware you're working with, right? Because we're talking about machines that have huge GPU capabilities, right? So encoding, expensive encoding, that's fine, right? As long as it gives you the accuracy or the rate that you're desiring, that's okay. But then you also have very, very small devices where it may only have a little bit capability for a couple of neural network layers, right? So what do we do in this situation? We can't spend a lot of complexity built into the encoder side because of what it can support. So there is, I think, a lot of dynamics, adaptability that the system needs to be built, and that's one of the reason why, if you look at it, the different standard work like the MPAC, JPAC, they have been quite active forming these ad hoc groups looking at video coding for machines, for example, with MPAC, and there's an AI ad hoc group, with JPAC too, because essentially this becomes quite challenging to think about from a standardization point of view, right? So yeah, there's a lot of, I think, interesting work that needs to happen, not just for us who are in academia, think about, well, how do we best solve this problem? How do we design the algorithm that can serve these different purposes? But also from the more engineering or the industry point of, well, if we have this great algorithm, how do we deploy in our system, in our devices, right? So I think it's although it's very exciting, but it is also very complex and although very difficult problem.
Yeah, I think that's why we're talking here, because there's a lot of suspicions actually from the industry that whether the use of machine learning or AI can ever benefit the codec world, image codecs or video codecs. But talking with you guys previously, and we learned that sometimes, for example, here Zhihao talked a lot about transforms. I heard you once mention that at one time you're trying to get some new algorithms for transform, and then submit some paper to in the academia area, and then some reviewers challenge that you should put the transform within the real codec framework and then do some benchmark to show the advantages of the algorithms. But indeed, image and video codec, if you really want to go down as what standardization or the industry are trying to evaluate, it could be hard because there is kind of a complicated. So if you design some new algorithm, just how, for example, you have some new algorithm, and then you are seems like obligated to put that module within the whole framework, and that takes time. So what do you think? Uh, how the academia can really advance some algorithms without actually being hindered by a lot of simply industrial criteria, because we need pioneer work from the academia so that I can guide or give us some insights, eventually benefit for example, the codec in the industry. But on the other side, the industry has a lot of suspicions. And then so they want to put a lot of policies or rules, hoping the academic paper can follow some benchmarking. So what do you think?
Um, yes. So first of all, that's a very good point. So I do agree. Like the learning curve for codec is very long. So at once I was looking into the BBC codec, um, but the document was like more than 50 pages, and it's very dense, and and it took me for like several days to run it for the first time, to like learn the documents and run it for the first time. So so yeah, so it do have a like long learning curve, and regarding the
Well, that also doesn't include making changes, right? So, sorry for the interruption. I just want to make a point. So Zoe mentioned about the story. I told her about, this. It's not actually our group's work. It was someone that I know also been working in this area for a long time, but no longer as active because. Um, they want to propose something new, and this particular still within the traditional framework of, let's say, perhaps a new block transfer, right? But the problem is that anytime you want to make a change to the transform, it is the core, right? So that means that everything else downstream will have to be changed. And how do you do that, right? How do you signaling? How do you do entropy codings? So all of that's not gonna fit in the existing, block-based transform paradigm, in any modern codec. So it's I think it's because how everything is so related. A small change in one place, perhaps you would imagine it's a small change. It could mean that many change in other places. And as academians, we publish papers and we get reviewers, and then reviewer has different background. Now, if they don't necessarily come from the coding community, they may not understand. They could say, well, yes, this looks good mathematically. You proved it. It's better, than existing ones. But I can't see this berry savings. I don't see the RD curves. I don't see your BDPSNR, right? So, but in order to do that, you have to put in a existing a coding framework to be able to show that. So I think that's where, from the academic point of view, it's hindering, and that's why people who might be working on this for a while and then just feel hopeless. So that's one aspect. And that I just kind of wanted to point out that the challenge is not necessarily because in academics we only wanted to pursue papers, and then we don't care about how we could I would say it's more of like how do we deliver what we think is great into a actual product or deployment, right? Or even before that, to have people agree with that what is right, or what is whether it's a potential a pathway. So I think it's important. We need understanding from both sides. So go ahead, Zhihao.
If I could just,
Oh,
one comment
Thomas, go.
was, I mean, having been participating in standardization, I would also say even within standardization, it's very difficult to make changes because you are in a local optimum, and there's lots and lots of moving parts. So it's certainly very hard if you don't have the deep immersion in the codec standard you're developing or you're using. But you can find something that should work doesn't work because many things automatically adjust inside an encoder, so it can be super hard. I think one of the things that's really attractive and interesting about some of this AI stuff is that in a sense it can be simpler, that you have a lot of layers and then you have automatic training, and it's the training that takes care of all the very complicated hand tuning that you've talked about. And so that's why there's maybe we would get a fundamentally different architecture for future standards that is much simpler and less and yet more general with these kind of layered solutions.
Yeah, and I think one of the thing a little bit kind of deviate from this, but I think also is important, is we wanted to push for at many of these high profile conferences that we have attractions such as workshops, for example, or special sessions where we attract people from both academias and industry to meet and then to talk about these emerging areas, right? Both people from industry who think about how do I do this from the hardware point of view, and people from standardized bodies and say, well, this is how do we standardize this, right? So there needs to be opportunities and venues where people can come in together to talk about these things. So that's sort of, I think, another a way to bring people together. So I think that the challenge here is sometimes it's difficult, right? People work in industries who work with products, they go to certain conferences, they go to certain meetings, but academic people, we go to academic conference. So there is not a lot of opportunity to talk and chat about this. So I think that also needs to have a better environment to make sure that these emerging topics can be discussed. We can see the different challenges early on so people can work on these together.
Yeah. So you basically take the request from the industry and then can really just be aware of what the real issue down there and provide the solution from academia. And
Yeah.
that's very needed. But back to, because we all talk about like there's quite some challenges down there overall. And then back to our original topic that we talk about the best paper that you just won in the WACV, because this conference, in my impression, that is one of the, I think is one of the top also computer vision conferences. And there's only one, I think they have two tracks, algorithms and applications, right? So there's one paper of each track. But the majority actually submitted the papers were in the track of algorithm, and you won the best paper of the algorithm track. In one sense, because this is a computer vision conference, but the best algorithm paper actually is focused on codec. So we do see that at least in this trend, AI applies to codec actually draws this majority attention. So I'm just curious, back to the paper itself, what kind of algorithm in general that you proposed and what results that you presented to show some promising for the AI plus codec topic?
Yeah, so first of all, thank you for introducing our paper. So so in that paper, so we first identify the relationship between compression or coding with generative model. So generative model is a kind of AI model that learns the distribution of data. So it is fundamentally related to coding and compression because both of them aims to find patterns in the data. So I hope this made sense. But so I just want to I just want to highlight that the introduction of AI brings like a very sorry, let me do it again.
Sure.
So yeah, so I just want to highlight that AI bridges the gap between many fields, including coding and computer vision and machine learning. So I think like maybe in the future we can see that there's a single method for both coding or compression and image generating. For example, I think so. I guess maybe we know the diffusion models, the stable diffusion, like the AI art models. So like one sorry, Professor Zhu, like
No worries.
Yeah.
Because there's a lot of curiosity. They are just
yeah.
from the
Yeah.
industry as from the community.
Because I think there are like a lot of technical stuff and I don't know like what to
Well,
say
so
and what not
okay,
to
so
say.
maybe yeah, so maybe one way to think about this is I mean the goal here, if you look at so for this particular paper, what we proposing are to kind of think about the coding from the point of a very variational autoencoder, and that's one type of generative probabilistic model. Okay, and then as Zhihao says that it can learn the statistic distributions from the data. So in our case, that would be images. And we actually did it for image. We have not quite done it for video yet because, as you all know, they're much more complicated because there's also a lot of redundancies in the time domain, right? So that's something, yes, we're working on. The original paper in this conference is more focusing on the image, right? So if you think about it, all it tries to do is how do I transform data from the pixel domain to some kind of latent feature space, right? But that, if you think of it that way, it's really quite similar to in the traditional coding, the transform coding, right? But it is done in a way that, and then what we are able to show is that using these variational autoencoders, we can learn the rate distortion function of the data, and which is quite fundamental for lossy compression. So I think this is where it brings a new insight to the community, and for people, I think as Zoe mentioned, this is a computer vision conference, right? So the audience are familiar with variation autoencoder. So we're not proposing, a new neural network architecture or anything, and it has been shown really great for generating things, or transform from one type of things to something else, right? So these has been shown, but I guess what's new is people haven't think about its relationship to transform coding, for example, right? But because we work on compression, we see there is that connection, and then so I think that's where this paper got noticed, and people appreciate this new insight that we brought to the community.
So what kind of interested
Yeah, I
me
think
was the connection you made there between the older kind of fixed architecture that compression has and this sort of more general model. So if I'm understanding it rightly, these kind of generative autoencoders work by creating a set of what you call latent variables, which you can use to then generate an image at the other end. So it's kind of some kind of hidden space in the middle, and that's what you want to approximate, and that's what you want to do dimensional reduction on, and that's what you want to transmit. And then this is what a decoder can use to generate your image or your video. So you kind of have a matched pair of encoder and decoder
Exactly.
with these coefficients or variables in the middle, and that does sound very like conventional compression.
Yeah, and then you're right. And the other, I think, a contribution we have is if you think about it, so in the variation autoencoder, in order because we still have to do entropy coding, right? Because otherwise, this latent feature that we get from the VAE, it's continuous, right? So the entropy coding won't work. So that's another thing that Zhihao worked on to sort of update or modify the configuration, and this is particularly with the posterior and the prior distribution part that he has modified so that it can support entropy coding and make sort of this end-to-end lossy compression possible for building on this variation autoencoder. So I think this is where we kind of did something people feel that is quite interesting and brings new insights. And Zhihao, feel free to elaborate more.
So basically that's exactly what we do. And so one thing I want to highlight is that like the method developed from the perspective of like generative like version autoencoders is very similar to that of transform coding. So as we said, it's a generalization of the transform coding because so one way to think of it is that, for example, in JPEG we have a DCT and an inverse DCT, and actually there are like many types of DCTs we can, and when, for example, when designing a codec, we want to choose one type of transform over others, and but we may think like, why choosing this over others? So if we recall like DCT or other linear transforms, it's just a matrix transform, and that matrix contains a bunch of parameters, and what we can do is like, why not we just learn the parameters like using machine learning techniques. So, and if we make this transform like very complex, it becomes deep learning, and it becomes a kind of deep autoencoder. And and so by doing this, like we simplify we simplify manual work because we don't need to like try different transform configurations, and we just need to set a objective, and we just let the entire system learn the parameters itself, and it hopefully learns a very decent transform. So so this is one way to think of the autoencoders and the traditional transform coding methods.
Before that, I think we're talking about the autoencoder is on the computer vision field.
Yeah.
It's different from the encoder concept in the codec field. Go ahead.
I was just going to ask, I mean, you're talking about learning these parameters. Is this something that happens online as part of the encoding process, or do you do or is this in a sort of pre-trained situation? So could this system adapt in real time to the data that it's getting, or does it need to be trained?
Yeah, that's very insightful. So typically what we do is the pre-trained like method. So we have a model, we have a huge data set, we just train the model on the data set, and we use it and we keep it fixed forever. This is what we typically do. But there are indeed papers and like novel techniques doing it online. So what we could do is that first, so once we have a model, and once we are seeing new data, and we can design some algorithms such that if the model finds the new data follow a specific pattern, for example, it finds the incoming data are all screen data or all face images, then it can update its parameters to adapt to that model. And of course, this is done in encoder, the encoding side, and on the decoding side, we need some time to do the same thing, so that the encoder and decoder match each other. So yes, I guess this is one of the a promising future.
I remember some time ago there was an MPEG project called Reconfigurable Video Coding, where the idea was that you sent a description of your algorithm as part of the bit stream, and you could update it, and you can produce a rate distortion model that includes the entropy of your decoder algorithm as well as the data itself. But having this kind of general framework of video processing, where you are just sending weights of different layers and those kind of things that have been pre-trained, that does open a lot of interesting possibilities to send updated weights to decoders, as part of bit streams, and sometimes adapt, sometimes not adapt.
Yes, it is. So I would not say it's a like more general method like in AI, but I would say it's a very similar method. So in like AI-based coding, there are indeed methods that transmit like the weights of the model in the bit stream, and so on the encoder side, for example, what we can do is we just like overfit one model on an image, and we transmit the weights to the decoder side. So using the weights, the decoder can like perform very well on this single image. So this is what we could do, and some people tried that, and they got decent results. I would not say like state of the art or very promising, but they got decent results, and but like I would say it's a very interesting and like promising future direction in my view.
Can I learn, for example, we talk about this is promising. So what is the current performance compared to the traditional, because you're doing image codec for this paper and one the best algorithm. So I want to see, I think a lot of audience will also want to see what's the current result using this AI codec algorithm. What's the compression? Because we talk about codec, I think the image, we all know that we want to see to achieve the best quality, best possible quality, and then to have the least or smallest file size or bit rate. And at the same time, there's also the computational cost underlying during the encoding process. So what's the current performance that, based on your paper, compared to the state-of-the-art image traditional codec result?
Yeah, so in terms of the rate and distortion, our method is slightly better than the VTM. So it's the reference software for VVC. It's slightly better. It was 4% BD rate, so it's only like marginally better. But in terms of like efficiency or speed, like running speed, computational complexity, like learning-based methods are all very complex. So we require a GPU to run on. We need a GPU to execute our program. Otherwise, if we run on CPU, decoding a single, let's say, 512 by 768 image requires around half a second. So it's intolerable in many applications.
Encoding or decoding? Just you mentioned.
Just decoding, but
Decoding.
encoding is slower. Yeah.
Okay.
Yeah,
So basically, you mentioned 4% at least, right? Meaning that to achieve the same quality, and then there's a 4% bit rate gain, meaning that you're smaller by 4% compared to, for example, state art of VVC results, the H.264 from Tech side. But complexity is high.
I would say it's very high. It's far from, I would say intractable in like practical applications, and and that's a very huge problem for practical use of like learning-based codecs, and right now we are. So go ahead, Professor.
Yeah. So I think one other thing I wanted to point out is in this process we made an interesting discovery because in essence the decoding is progressive, right? So at a very low bit rate, we can already sort of seeing in general roughly what is the content in this frame, in this image. Okay, so I think this is, when you look at trade-off, I think it's important to know, and everybody knows that these, neural network-based compression is expensive because of the trainings and all of that. But I think that is not something can be necessarily improved purely based on algorithms and software. Okay, because that would also need hardware support and all of that. So that is something I think I have confidence that can be addressed down the road. Just maybe not right now. But what else? I mean, this interesting phenomenon we find, this is this progressive decoding, right? So essentially, it depending on what the application scenarios are, right? We could basically tailor this framework for different application scenarios. So we touched a little bit on, this concept of coding for machines, right? So at that, if this is, what our target application is, then perhaps we don't need, at, very high, bit rate to support, because we're not that interested in the pixel reconstruction aspect, right? If we can get the features, the content from the images or the video that is indeed needed for some downstream vision task, then we're fine, right? So in that sense, it could support these different scenarios, depends on what we use for. So I think there is also that aspect of generalization, and then how can it be applicable for the different application scenarios. And that aspect I think is also important to consider for this work
So
as well.
in comparing
I
these,
think this is a great point. That
in comparing these kind of algorithms with traditional compression algorithms, you're kind of fighting on your enemy's ground, as it were, because you're being assessed on pixel matched image metrics like PSNR or SSIM, which require perfect alignment. Would it be possible to get big gains and complexity reductions if you had to produce something that looked very similar but wasn't necessarily aligned in terms of the actual locations, exact locations of pixels and so on? Is there a degree of freedom that maybe you're not exploiting right now?
Yeah, I agree. So
go ahead, John.
Yeah, there's one small area of research in learned image coding is that generative image compression. So the objective is not to exactly reconstruct the pixels, but to reconstruct the pixels to achieve good perceptual quality. So one like very trivial or very simple example for this is to use like AI generative models. For example, if we have a image of grass, and we just save it as a text of a text consisting like a prompt saying an image of class, and in the decoder side we just use a like AI generative model to generate a arbitrary grass image, and then like if we look at the image, I mean the perceptual quality is like very high, but it's just not the original image. So that is one. So in some applications, it may be good. Yeah. So
Yeah, and then I'm sure Zoe now remembers we actually work on something like that, right?
yes. So basically, it's just combining compression and synthesis. So what Zhihao mentioned, that you get some certain information, and through the learning you identified actually get some knowledge regarding the detailed content, and they use the synthesis on the decoder or the player side to synthesize those textures. Actually, I think this is very great topic, that because based on what you found out in your paper, Maggie and Zhihao just mentioned that there's a progressive decoding. So I see actually at least the three benefits from progressive decoding that we just discussed. One is some of these video codec or image codec applications not just for human eyes, but for machine, because we compress the big amount of data, and finally we just want to communicate or get data shared and finally to be processed by machines. So machine may not need that perfect reconstruction, as long as some information that can be extracted is made good enough for machine, like what just Thomas mentioned. And secondly is maybe sometimes we don't have enough bit rate, right? So sometimes we have very low bandwidth. The situation of the network is not as good, but it still get some information, even for human eyes. And then just now we also mentioned that potentially because of progressive decoding, it can potentially combine with some synthesis work that actually reconstruct some images or videos on decoder side will actually at least present a great info, even though may not be completely fade out to the original source. So then that means that there needed some new metric, right?
Exactly.
And how do we evaluate the performance of such works? Any new like trends in academia right now? Because Tom just mentioned that you actually first your work has to be compared against existing work using PSNR, using SIM. That's basically pixel by pixel, just like original data, just reconstruct data. You try to compare them bit by bit to evaluate the result of this work. Some other works about along this line?
I think right now this is still at its infancy. So we know a lot of great people working on qualities on metrics, and then it hasn't quite, I guess, get enough attraction on this topic to have people think about work on that. But you're right. So that's one of the reason why I'm advocating to have both in academia and then that's my familiar territory, to bring people together, right? To try to say, hey, here is really cool. We have a lot of new idea. We've done some groundwork, and then we've seen some promising things that could happen. Now how can people who understands about standardization, how can people understand about the qualities, can help us think about these, because this needs to be addressed. Like you said, we're still using the same old metric for evaluation, right? And then that may not be fair because we're playing other people's playground in their sandbox. So we need something new. So yeah, so this is all I think will be happening very soon. We've seen quite a lot of other groups around the world that are interested in this problems. And hopefully, with a little bit more critical mass, we can move this forward a little bit faster.
Well, thanks for the sharing. Actually, I think right now we have talked quite a bit, and in sometimes we used to talk about quite some deep technology and algorithms. So I'm here try to ramp up this. Even though we still have a lot of things, I'm actually really enjoyed, and I like to actually for the first time to have each of you uh, to at least share something about your thoughts on AI or machine learning on codec. And I may want to go to Maggie first, and then because for here you are professor, and then you can have many topics to explore. And then I know that from the website and then from the bio of the paper, and you have touched a lot of areas. And then machine learning to codec. What's your thought? And that's just one point, good enough.
Yeah. So I think to me, there was a great paper by Professor Erdelp that talk about. So the question at the time, that was not really too long ago. I think maybe less than 10 years ago, and people think compression is dead, right?
Mhm.
So he and a couple of others wrote a paper and said that's not the case. So at that time, of course, machine learning hasn't becoming as popular or as of trending topic yet, but it was at sort of a dark place for academia, because there is no work left for the academia to do, except yes, there are small problems, there are certain applications we can work on, but there's from a point of view from academic contributions to the community, it becomes very difficult. right? And then this also is related to how do we find students that are interested in working on this problem? How do we find funding agency sponsors to sponsor the work, right? But now, with this growing trend of AI and machine learning, and I've been asked, so I have some industry experience, and at the time, since people know that I have some compressions, they always ask, what's different, right? What can be new and then groundbreaking? And I don't have an answer at the time. But now I think as we start to pick up the work in this space again, I see hope. Um, and I, and then this is to me, where really, I'm very interested. I do a lot of things, but this is something that is to me very hold closer to my heart, just because of where my training come from, right? So I do hope that we can attract. We need more people. We need more people who are interested in working on this problem, and we need people who have different domain experts so that we can answer all these hard questions that we talked about today. So that's my 2 cents.
Wow. Yeah, we see. Oh, we're all looking forward to the future, basically. And then back to Thomas, because you have been actually working this area, especially for standardization, and from HEVC to AV1, and then you have heavily involved in the standardization, but you also heavily involved in the codec product for all these many years. So what do you think about
I think
AI?
it's really exciting, and I think we touched really on one of the sort of the key roadblock at the moment is metrics to assess the true potential of these algorithms. I think we don't have a really good metric for subjective quality. There's been lots of good work, say with VMAP and so on, for trying to assess things better, but they're still kind of pixel mapped. And for a long time, people have been wanting to introduce synthesis algorithms into compression. So I think that's one route to a kind of hybrid ML, non-ML kind of codec. But the other thing that is really exciting is these very general autoencoder architectures that can introduce at least not computational simplicity, but conceptual simplicity into this whole space when our codec standards have got very, very complex and hard to optimize. So I see these two major features that will progress in the next few years.
Well, thank you. You're talking about the complexity of the codecs as well as we do need a metric. I think talking about metrics is one more common that because VMAP seems at least right now has been widely used, which was originally proposed by the Netflix team. Actually, it's also leveraged machine learning. So actually, when we try to evaluate machine learning applied to codec, and we need a metric, again, we may rely on the machine learning development to find out a codec or objective codec that we are talking about to be really leverage the subject, which is a human eyes justification, or maybe not aligned with the human eyes justification, but aligned justification from the machine side. So there's a lot of machine learning actually involved that I see. Last, but of course not least, Zhihao, I'd like to have your opinion because again, you are the third year student into the PhD program. Now I have to say that it's very, what you've done has been very impressive. And then you won a best paper finalist as a first author. And then again, for this year, we're talking about that WACV, and you won, with your co-authors, won the best algorithm paper. Again, you as the first author. So not only just for the direction of AI, but codec, I want to talk a little bit, like you have some sort about your career that you think about academia, industry, and what do you think? Of course, related to what the work you have been doing, or you are going to continue to work on AI plus codec. So what do you think you foresee your future? Maybe not too much, 3 to 5 years?
Yeah. So for me personally, I am more interested in a academic position because I kind of I enjoy like doing research. I enjoy like exploring new things,
Mhm.
and but so for like industry, I also like engineering. I also like tuning parameters and make things work. So it's very important. It is what made the world like work. Um, yeah. So like both of them are very like interesting. But for me, I just um, uh, like so when I was a child, I wanted to be a teacher. So like I will uh, I personally like prefer like an academic job like more.
Yeah,
Yeah.
you really enjoy, like you want to be teacher, and then also you want to do the research. Uh,
Yeah, that's
and
true.
then what do you
That's
think of the research direction of AI plus codec?
so so there are like many like interesting and promising like directions. So I would say in general there are three for codecs plus AI. There are um, codecs as we said, there are codecs with AI. So we can use like AI techniques to improve codecs. There are codecs for AI. We can like design codec like coding algorithms specifically for AI
Hmm.
instead of human. And there are another one, namely codecs of AI. So right now AI models are very huge. It's very big, and there are an area of research that is like coding of AI models themselves. So we are not coding images, we are not coding videos, we are coding the AI models, the weights of the AI models themselves. So it's coding of AI, and so like I think all of those three are very interesting and promising, and um, they might not be useful in the current world, in the current state, but um, I believe like maybe it's 5 years, maybe it's 10 years, maybe it's 20 years, but like eventually they will play a role in the industry. Yeah.
Well, thank you. And actually, thanks everyone for getting to this. I think it's very exciting and insightful uh, episode. So we talk about the three things. Just to echo what Zhihao has just mentioned. So we talk about a codec for AI, codec with AI, and codec of AI. And then, of course, there's a lot of work and a lot of hope and something to look forward to. So thanks everybody, and from a different corner of the world that to join this episode. So, and
Thank,
thanks for our audience. And
yeah, thank you,
Thank you.
Zoe, for inviting and hosting us. And then thank you, Thomas, for the great discussion.
Thank you. It's really, really
well,
interesting. Thanks.